So this will probably be the most mathematical and technically involving session that we've done so far. And when I was first starting to do these things, it was really unintuitive to wrap my head around this Bayesian analysis. And so it might not make sense at the first glance, but at any point, if you guys have any questions or like if anything doesn't make any sense, we can just stop and reiterate over those ideas just to make sure we're all on the same page. So
Okay.
okay. Okay, can you all see this?
Yes. Yeah.
Okay. So have the chat. Awesome. Okay, so I've also got the chat next to me. So if you guys want to chat or unmute yourself or anything, like anything works. Okay, so today the topic of the session would be Bayesian inference using Markov chain Monte Carlo. And okay, let me just see if I'm recording this. Okay, awesome. So this will be our final session in the workshop series in machine learning using Python. And okay, so this is a code by a professor of psychology. It tells us the importance of Bayesian school of thought. The whole field of Bayesian analysis has very philosophical origins, which is crucial to understand for any critical or scientific thinking. As researchers, we should be aware of the role implicit biases play in terms of understanding how we analyze scientific data. And I think Bayesian analysis gives an interesting glimpse into this analysis. So he says critical thinking is an active and ongoing process. It requires that we all think like Bayesians, updating our knowledge as new information comes in. So this can be thought of as a philosophical interpretation of the Bayes rule, but I thought that was really interesting. So let's see more into how this plays out mathematically. Okay, before I'll just present a brief outline of then all the topics that we'll see in this session. So we'll begin with the Bayesian versus frequentist definition comparison, like in terms of probabilities. So the traditional way of thinking, we are more inclined to think about probabilities in terms of frequencies and not in a Bayesian sense. So then we'll see a bunch of practical and philosophical examples of how the differences between these two definitions of probability play out. Then we'll see what is Bayesian inference, and we'll see Markov chains and Monte Carlo methods. And we'll combine both of those together and see what is Markov chain Monte Carlo and see how we can sample using Markov chain Monte Carlo. Then we'll see a bunch of examples using MCMC and how MCMC is used traditionally. And finally, we'll see mechanical engineers and where do we use MCMC in our research. Finally, we'll have the tutorial on MCMC in Collab. So there is a tutorial on MCMC which is pretty standard. So we'll not be getting like really into details, but we'll basically go through the code together and see if we can understand like what's happening and how we can implement MCMC in Python. So that'll be a very brief tutorial. And okay. So let's begin with the frequentist versus Bayesian definitions of probability. So if we are working in a data-intensive research, it is pretty common to come across terms like Bayesian approach or a frequentist approach. So Before diving deeper into Bayesian inference, it is first important to establish the differences between these two modes of definitions. So for frequentists, this is the common understanding that we intuitively have in terms of probability. It is defined as the limiting case of a repeated measurement of an event. So if you have a coin, we toss the coin like 100 times and see how many times they are heads and the number of times they are tails. So if we have 50 heads, then we know that the probability of getting a head would be 0.5. And so we can say that probabilities are related to the frequency of an event in a frequentist approach. But for a Bayesian approach, the probabilities are fundamentally related to their own knowledge about an event. That is super vague, and when I first came across that, that didn't make any sense to me. So, for Bayesians, probabilities are more uh, intuitive, and they essentially say that based on the prior knowledge that I have, I'm coming to a conclusion that the probability of, let's say, getting ahead in a coin toss is roughly 0.5. And I have my own reasons for saying that, but it doesn't necessarily have to be from flipping a coin or observing the number of times we got ahead and so on. But it is important to mention that they could make their conclusions based on the frequency of an event, but that is not the fundamental thing. So for Bayesians, it's essentially an idea or a value which they arrive at somehow based on their intuitions and their prior knowledge of an event and so on. So let's try to make sense of what that means more precisely. Um, let's have a cheat sheet like on the top. So for frequentists, it's frequency, and for Bayesians, it's beliefs based on which they make probabilities. So let's see an example. If we are measuring the flux of a star, uh, if we are let's say the scientist in our example is an astronomer and he's observing the flux of a star from a faraway galaxy using his telescope. So now say he has made n measurements. If the astronomer was a frequentist, he would say the probability of the flux being a certain value would be the frequency uh, in which this value appears in his measurements. So if he were to say if he were to check the probability of the flux being 100, he would see the number of times he had like the measurement 100 in all the n measurements, and he would just say like if he had k hundreds in his measurements, he would say k by n is my probability. So it is important to note that it is not valid to talk about the true flux of some quantity in a frequentist approach, as the frequency of something can, which is true or constant, doesn't make sense to have a frequency of something which is constant. So true flux is meaningless in a frequentist approach. And in a Bayesian approach, the goal is to update your beliefs on probabilities by using some measure. So for a Bayesian, it is a perfectly logical statement to say that the flux of a star is 200, let's say, with some confidence interval, even without measuring anything. Maybe 200 might be the most common flux which comes out of stars in a particular galaxy that he's observing. Or alternatively, he could also make a conclusion based on the frequency of his measurements to update his beliefs. So so in this approach, interestingly, it is valid to talk about the true flux of a quantity. So say a Bayesian here could say that the true flux is 150 with a 10% error range. So that's his belief which he arrived at. And this arguably subtle difference leads to like dramatically different differences while implementing this mathematically. So does that kind of make sense? The differences between a frequentist and a Bayesian definition of probability. Or
I
okay,
think I get the idea, but I need to see like the concrete example to see how they're different.
okay, we're in luck. I think we have an example. Okay, yeah. So while measuring the frequency, right, we know the definition for a frequency. We know we have these measurements and we know how to calculate the frequency mathematically. So how do you do this? How do you integrate like your prior knowledge or some conclusion about your prior knowledge into a mathematical formula? So this is where the Bayes rule comes in. And so when Thomas Bayes first discovered this theorem in the 1750s, he thought it was so insignificant that he didn't even care to publish this idea. And it was only later identified and published posthumously when people went through his work after his death. I think he passed away in 1761, and a posthumous paper was published in 1763, which had like one of this formulas. So I know we've all like come across Bayes' rule at some point during high school or in some introductory probability course, but let's have a brief refresher just to make sure that we're all on the same page. So in a Bayes rule, we have the LHS, which is the posterior probability. So this is the probability of the model given some data. So this is P of A by B, which is read as P of A given B, where B is some data which we have. And P of this is equal to the P of B by A into P of A by P of B. So P of B by A is the likelihood function. So this is directly proportional to the likelihood definition. So as a note, I've added the definition of the likelihood function. So, and P of A is the model prior. So this is the knowledge, this is all the knowledge that we have about this model even before we start measuring things. And then P of B is the model evidence, which is basically a normalization term. And for simplicity and understanding things, we can ignore this during calculations. So frequentists don't have a problem with this formula itself, but they have the problem with the Bayesian interpretation of probability implied by the P of A by B term. So while the whole thing makes sense to them, they disagree that P of A on its own can have any meaning without taking any data. So so the P of a standalone probability of the model doesn't make any sense to them without having any data. But this would be possible in a Bayesian sense, and this is where we have all our prior intuitions and so on. Okay, so the fundamental takeaway on the differences is the following. So we have a frequentist approach where we have variations of data and their derived quantities and a fixed model. And on the other hand, for a Bayesian, we have variations of beliefs about the model and a fixed data. So we have data and a model. So in one, we are varying like data, and the other one, we are varying the model. So in a sense, it looks like we are working on the opposite ends of the spectrum, but we are, however, these are not entirely different. For reference, I have the Bayes rule in the bottom. And a form of optimization using the frequentist approach, the uh, the F is the likelihood maximization, and a form of optimization in a Bayesian approach is posterior maximization, where we maximize the whole thing. So a posterior maximization is basically the likelihood and the prior maximization. So we can see that if we have a flat prior, if we have a uniform prior or an uninformative prior, then we know that the P of A is 1, and the posterior essentially boils down to a likelihood. So in an uninformative case, a case in which we are not using any of our prejudices or biases, In that case, a Bayesian analysis would roughly be equivalent to a frequentist approach. So we can call that the frequentist approach is basically a particular case of a Bayesian interpretation. So we can say that it is more rigorous and it is more informative in terms of including a broader set of knowledge on the idea which we have about a certain model. So when we've seen where they would be the same. So if we have a flat prior when P of A is 1, then we know both of them are the same. But where would they be drastically different? The important contribution is the uncertainty quantification. In Bayesian analysis, we can have pretty valid bounds for uncertainty. We could have confidence intervals and we could see the variances of distributions and so on. So while doing uncertainty quantification, like Bayesian analysis is way more helpful than frequentist analysis, and also in handling nuisance parameters. So nuisance parameters are latent variables which don't necessarily show up in mathematical terms, but ultimately affect the final conclusions. So okay, so let's see the formal definition of a Bayesian inference. Let's define statistical inference first. So this is a process of using data analysis to infer properties of an underlying distribution of a probability. So we are using data analysis to understand the probabilities of a distribution, like the mean or the variance of a distribution and so on. So in a Bayesian inference, it's basically statistical inference, but with the help of Bayes rule. Okay, so one method to implement Bayesian inference is by using Markov chain Monte Carlo. And as the name suggests, it is made up of Markov chains and Monte Carlo simulations. So what are Markov chains? The definition is Markov chain is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state of the previous event. Okay, so let's break it down into smaller chunks. So the Markov chain was proposed by a Russian mathematician called Andrei Markov, and he basically explains the probability of getting from one state to the other by using a state diagram. So this is the state diagram of a hypothetical case. So we have n+1 states, and if we look more closely, we can see that the probability of going from 0 to 1 would be p0, 1, and the probability of staying in the same state would be p0, 0. And similarly, we can see that there are probabilities to go from 1 to 1 and 1 to 2 and like n+1 to 1 and n to 0 and so on. So this is a really big example. So to make more sense, let's look at a smaller example. Let's say we only have 3 states, A, B, and C. And then this is a state diagram, which is a Markov chain. And this Markov chain can also be represented by a state transition matrix. So we have a state A, and the probability of going from A to B is 0.1, and the probability of going from A to C is 0.9. And for the sake of completeness, we can make sure that the probabilities add up to 1. And similarly from B to C and B to A and so on, like these add up to 1. And if we look at the corresponding matrix, right, we can see that this is the A and eighth index. So if we look at like AA, we know that the probability of going from A to A is 0 since there are no loops, and from going from A to B is 0.1 and 0.9 and so on. So basically we can have a pretty mathematical idea of these diagrams, which should be really helpful when we are like manipulating things. And an advantage of using NumPy is they are really good with handling matrices and so on. So we can implement like basic Markov chain interpretations using NumPy. And so now let's look at a Monte Carlo simulation. So what is a Monte Carlo simulation? I think an easier way to visualize is through an example. So let's have a look at this example, and let's say we are trying to calculate the value of pi, and we have a square with a unit length, and we have a fourth of a circle inscribed into the square. So if we compare the ratio of areas, right, of the area of the square and the area of the quarter circle that we have, so this is like 1, and the quarter circle would be pi r square by 4. So that's pi by 4, and so it's 1 by pi by 4, and so on. So if we have the ratio of these areas, we can get a pretty close estimate of pi. So we can see that if we start sampling points, if we just throw a bunch of points randomly in the square, and we look at the number of points that are inside the square and the number of points that are only inside the circle, then we can make a vague estimation of the areas of the surfaces. And we can see that as we increase the number of sampling points, the value of pi gets really close to the true value of pi. So I think this is a really interesting way to calculate the value of pi. We could just do it in a couple of lines in Python. So is this clear, like so far, like the Monte Carlo simulations and the Markov chains?
It's clear. I just have a quick question. What assumptions do you have to make in order to use the Monte Carlo Markov chain?
Yeah, so there are a few assumptions which we have to make. I think the first one would be, if we have a Markov chain, we want it to be, we don't want this to have a loop inside it. So if we, since we are using Markov chain Monte Carlo to sample the whole space, so we don't want to be stuck at any single state. So if there was a loop, and once you go to a certain state, and you can only like keep moving within these three states and not go back, then that would be a case where MCMC would fail. And the other one would be, oh yeah, I think we actually have a slide where we actually go over all the conditions that we have to hold to implement MCMC. I think it's in a couple of slides down the line, but I'll get back to you. Anything else? Okay. Let's actually go through that first. Oh yeah, I think the other one is, it has to be irreducible, where there must be a positive probability to go from one state to the other, and they should also like hold the Markov property, where the current state can only influence the next state. So if we have this whole chain of Markov chains, then this S state can only be influenced by this state, and this can only be influenced by this state, and it doesn't take into consideration all the previous states, and it only cares about the last state, and that's it. I think if we have these three properties, then we can do MCMC. Okay, so let's see like what MCMC actually is. And so now that we've seen like what a Markov chain is and what is a Monte Carlo simulation, let's go back to this example where we have three states and we have a state transition matrix. So a Markov chain Monte Carlo is basically how you can move from one state to the other by using the state transition matrix and by sampling the going from one state to the other using Monte Carlo. So let's look at an example. So if we begin with a random state A, then we know that we can go to the state B with 0.1 and state C with 0.9. So we do a random sample. So we do a Monte Carlo simulation to go to either A, B, or C. So let's say we generate a random number between 0 and 1, and if it's less than 0.1, then we go to B, and if it's more than 0.1, we just go to C. So the conditional probabilities are defined by the Markov chains, and the next step that we go to, or the sampling from A to the next step, this is defined by the Monte Carlo simulation. So that's so once you begin at a state A, you could have a number of Markov chain Monte Carlo samplers. So this is one sampler which began at a state A, and you keep on sampling, and then you go to state B, and so on. And the I think the crucial takeaway is to note that despite having different initial conditions, or despite having the same initial conditions, like even if you begin at A and A, you will end up with completely different chains. So this is because of the Monte Carlo aspect. You are doing a random simulation. So if you have two different chains which begin with the same initial conditions, you'll end up with totally different chains. So this is a Markov chain Monte Carlo sample, and each sample is basically trying to understand the distribution which is governing these states. So our goal from MCMC is to use the conditional probabilities like P of X by Y. That is the probability of getting to B using A. So that's a conditional probability. And we're using these conditional probabilities to understand the joint probability distribution. So a joint PDF, this P of X comma Y, this gives the most complete set of information about these variables. Since if you have P of X comma Y, you can also get like P of X and P of Y. So this would be like a like imagine a two-dimensional Gaussian, and if you look at the projection on the x-axis, then that would be the P of X, and the projection on the y-axis would be the P of Y, and so on. So we are basically using these data, and we are using these chains by sampling, and we are trying to arrive at a joint PDF, which gives us the most complete sense of these variables and their state relations. So that's essentially MCMC, and let's look at a practical example of what MCMC does. So let's say these are the given conditional probabilities, and we are trying to predict the probability of it being sunny or rainy. So we know that if it was rainy yesterday, we know that the probability of it being sunny would be 0.5. And similarly, if it was rainy yesterday, the probability of it raining again today would be 0.5, and so on. And we can see that they add up to 1, since they are the only two options that we have. And again, like if it was sunny today, the probability of raining tomorrow would be 0.1. And the last case would be if it's sunny yesterday, it's going to be sunny today with a probability of 0.9. So given that we have these conditional probabilities, and they do satisfy all these properties which we have, then we can try to predict the probability of it being sunny or rainy, like independently, like in terms of a joint distribution, by using these Markov chains. So we'll begin with the probability of, let's say we begin with an initial state of S, and the initial state is actually it doesn't matter like what you take. No matter what you begin with, you will eventually stabilize at an equivalent distribution. Like the chain will eventually stabilize at an equivalent distribution, which is governed by these terms. So you could have 100 chains. So if we have seen in the Monte Carlo simulation, we had like thousands of points, right? So, and each point plays a part in evaluating the value of pi. So similarly, each point is analogous to each Markov chain. So this is called an MCMC sampler. So we begin with an S, and then we roll a dice or we generate a random number between 0 and 1. And if it's already sunny, we'll base our results on these two probabilities. And if it's less than 0.1, then we say it's sunny. And if it's more than 0.1, we say it's sunny. Yeah, if it's less than 0.1, we say it's rainy. So it makes sense that we had randomly arrived at a sunny day after a sunny day. And now if it's sunny, we do a Monte Carlo simulation and see what the next state would be, and so on. We keep moving forward, and these can have like an infinite length. And the idea is that they'll essentially boil down to a probability which would be governed based on these probabilities. So if we have all these simulations, right, then we can simply calculate the probability of it being rainy or sunny. So based on this chain, we can basically see like there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and there are like 1, 2, 3, 4, 5. So we can basically say like 5 by 16 is this or something like that. So finally we can arrive at the uh, P of S and P of R independently without the use of any conditional probabilities. So that's basically the crux of what we are trying to do in an MCMC. And these can get like really complicated, but this is the soul of what's happening. So does that make sense, or do you guys have like any questions in this example? Okay. Um, Okay, I also want to present like a really graphical interpretation of what's happening. So I found this really cool GIF online. Um, so let's say we have two different variables, right? So like sunny and rainy, if we have two different variables, like the sigma and the variance, so the mean and the variance, and we take like three different Markov chains. They are represented by this violet, red, and blue. And we are trying to learn the bivariate Gaussian distribution. So as we can see how we are, we can see the learned probabilities in this example. So we can see that as they begin randomly at some initial state, we can see that they begin at like completely different initial states, but all of them end up producing the same distribution. And we can also see that the initial chain, the initial length of the chain is completely out of sync with the distribution which we are trying to find. So so I think this is an important step to note. So there is this term called a burnout or a burn-in step, where we essentially ignore the first couple of hundred iterations just to make sure that we don't have any effects of the initial conditions into the final distribution. So so yeah, so basically we use these samplers and we arrive at a posterior density. So this is the joint PDF. So I told that to move from one step to the other, we basically generate a random number between 0 and 1, and we see the probabilities and move forward. But that was a really naive way of implementing Monte Carlo, but there are really complicated sampling techniques. So these are all the ways in which we can do Monte Carlo. So, so the first one is called Metropolis Hastings sampling. So this is implemented in the PyMC module, and we'll look into the Metropolis Hastings sampling in the next slide. But there are also a couple of other things. Like we also have the affine invariant sampling, which is implemented in the MC module. So this is what we'll be using in our example in the tutorial. And we have a really popular Gibbs sampling, which is used in Hop MCMC module, and the no U-turn sampler, which is used in PyStan. So Stan is a statistical language. If any of you guys are working on, you can actually write Stan code into a Python module, and you can do the analysis using Python, and you can define your log likelihoods, and the log prior values using stan. So this is a mix of both, and there are like a bunch of other things which do like really amazing sampling techniques. So the Metropolis Hastings sampling is basically you have a ratio R, and so in the previous case we had a chain which went from sunny to rainy to sunny or something like that. So how do we go from like a state to the next? So we basically take the ratio of the posterior probabilities of the new state and divide it by the old state. And we know that the posterior is prior into likelihood. And if the ratio of the posteriors is greater than 1, then we accept the new case and we move forward, like we sample with this point. And if the ratio is actually less than 1, then we accept with an R probability. So what do I mean by that? If the ratio is 0.8, then since it's less than 1, we accept it with a 0.8 probability. So this is really simple, and it it can be really effective. But the only drawback is by doing this is we have it takes a longer time to stabilize and arrive at the distribution. So we have this is highly dependent on arriving at really good initial conditions randomly. So we always end up burning a lot of the initial stages. So does that make sense? Like the Metropolis Hastings sampling? Would you guys want me to go over this like once again? Okay, awesome. And yes, so why do we need Markov chain Monte Carlo? So doing multi-parameter optimization is always really hard, and I couldn't find a better example than this to see why it's hard. So you start tuning one parameter and the other one blows up, and you end up spending a long time trying to find the global minima or the global maxima. So multi-parameter optimization is an extremely hard optimization problem for traditional optimization techniques. And MCMC does a really great job at finding the optimal case. And also, as we have seen in MCMC, uh, the MCMC solutions are all probability distribution functions. Like a traditional optimization, like Newton-Raphson might say, the optimal value is 0.5 or something like that. But an MCMC would say that the optimal value is a PDF. So it is a probability distribution function with a mean of 0.5 and some variance or something like that. So you basically have an idea of the variance. Since you have a PDF, you can say you can understand the parameters of the PDFs, like how sharp the mean is or how bad it is varying. So by using the variance of the PDFs, you can make an estimate about the uncertainty of your solution. So the takeaway is MCMC is really good for multi-parameter optimization and for uncertainty quantification, which is really important for modeling like dynamical systems or turbulence modeling or a lot of other things. Okay, so let's look at a few examples of where MCMC is used in mechanical engineering. So I've been using Bayesian Inference for the past year and a half, and it's working really well. So if any of you guys are like in fluids, this was our latest talk at APS, where we presented an approach on identifying vortex properties using Bayesian inference. So we were trying to identify hairpin vortex structures from boundary layer flows using. So we had some PIV data which we collected from the Harris wind tunnel, and we were trying to identify hairpin vortex structures and make an analysis of the properties of the boundary layers and the turbulence, Reynolds stress field, and so on. So at the core of, so this is basically a Bayesian framework, and this framework is available online. This is hosted on this link. And if any of you guys are working on turbulent fields and you want to try to analyze like some properties of your boundary layer flows, you can basically use our code and get a view of the properties of your boundary layers. And we also have another turbulence example. So in this paper by Karthik Juraswamy from Michigan, the numerical and so we have numerical and experimental data which we use to model and reduce uncertainties of some proposed turbulence models. Since we don't have a closed form solution for turbulence, we usually try to come up with some model which satisfies like which closely agrees with the data that we have. And we need strong uncertainty analysis to see how well our model captures the data. So this paper provides a review of all the Bayesian techniques which you could use to model uncertainties and test the performance of your uncertainty and the validity of your model. And in this paper, they review Bayesian inference and particularly how MCMC is used in various fields like cosmology, mass spectroscopy, and surface physics. And it also covers topics like background subtraction and automated outlier detection. So a lot of cool things using Bayesian inference. And finally, we have this paper on how MCMC is used for converting like really complicated data from nonlinear systems into segmented linear systems based on switching linear dynamical systems. So if you are working in controls, I think this will be really interesting. And I think all of their code is also available online for you guys to play. So here are a few references. And so the first one is really short and clear explanation on MCMC. So this was like the best explanation on MCMC that I could find online, and it's only like 12 minutes. And this is a professor from UT Austin. And the next one is a paper on the fundamental differences between Bayesian and frequentist approaches. So this was written by Dr. Jake Vanderplas. He was a PhD student at UW, and he has like 50,000 citations or something by now. And so this is a really interesting paper which has a lot of philosophical examples on the differences between a Bayesian and frequentist approach. And he also gave a talk on the same paper, and it's on YouTube. It's like 26 minutes long, and this was a sci-fi talk. So if you don't want to read the papers, you can always watch the talk. And finally, if you really want to get into Bayesian inference, this is the textbook for Bayesian analysis. This is by Professor Andrew Gelman from Columbia. So this book has like 30,000 citations, and it's really impactful. And if any of you guys follow Veritasium on YouTube, he also made a video on Bayesian trap, which goes into the philosophical interpretations of Bayes' rule, and it's really interesting. And it's only like 10 minutes. So if you guys want to watch any of these things, you should definitely explore them. So yeah, so finally let's look at a small example on how we can use Bayes' rule. And okay, let's have a quick run on the code and let's see how it works. So all of this code, as I have mentioned in one of the slides, we'll be using the MC Python module, and I'm basically explaining, like, I've referred to this example from their own site. So yeah, before we like look at the example, was there any idea or point which is kind of vague or which didn't really make sense, which you would like me to go over? If there's anything, then we should totally do that like before moving to the tutorial.
I think it all made sense. I get the theory of it. I'm just confused on how that actually like translates to actually using it with real data. So I think the example should answer my confusion.
Okay, so would looking at a like an example like clarify that?
Yeah.
Okay. Can you all see this?
Yes.
Awesome. Okay, so so when I'm sharing the PPT, I'll also share the official link for where I've taken this code from. And so we'll begin by, so these are all in Collab, so that we don't have to install anything. But there are a bunch of things which Collab doesn't pre-install for us, since MC and triangle, these are all really specific to Bayesian inference. And so we can just say, we can have command prompt commands in Jupyter Notebook if we just add an exclamation in the starting. So we can just say exclamation and start writing like bash script code for Windows. So let's begin by installing the MC module. So MC module does the MCMC by taking the affine invariant sampling technique, which is very similar to like the Metropolis Hastings things which we have seen. And the triangle and the corner plots are used to like visualize the Bayesian results and make better sense of them, since they can get quite hard to understand if we don't have a proper visualization. So we have installed MC. Now I'm importing MC. Now, in this example, we'll basically do a linear regression using MCMC. So if we have a regression problem, then how do we use MCMC and find like the parameters of the interpolation? So for any example, we need some data. So I'm creating a function with so I'm taking 20 points, and I'm basically using this rule. I'm basically saying z is equal to alpha plus beta into x plus beta y into y. So this is a two-dimensional function where I'm taking the x and y values and I'm adding a y-intercept, and I'm also adding some normal noise just to make it a bit harder. So let's see the kind of data which we have. So our function basically depends on both x and the y values. So in one plot I have plotted the z and the x, and I have plotted the y values in terms of this color. So for a high y value, this would be higher, and for a low y value, it would be low. And this is the variation along the y-axis. So this is the data which we have, and we are basically trying to do a regression analysis and find like the line which makes this up. So if we have this data, can we go back and extract our alpha, beta x, and beta y values? So that's the question which we have right now. In fact, MCMC can also extract the variance of the noise which we have added. So our problem is basically we have a model. It takes 4 parameters: the alpha, beta x, beta y, and the epsilon, and it tries to generate some data. So our goal is to basically use MCMC and use this data to go back to finding these parameters. So this is all for data generation, and so this step is not part of MCMC. So okay, so this is the kind of data which we have, and now as we have seen, at the core of MCMC is the Bayes rule. So we'll begin by defining the prior function, and we'll define the likelihood function, and we'll define the posterior function. And for the sake of simplicity in calculations, we'll do logs of all of them. So it's log prior, log likelihood, and log posterior. So the simplest thing is log posterior. We know that a log posterior is log prior plus log likelihood. And so for simplicity, let's also take an uninformative prior. Let's take a flat prior. So this basically says if the variance is less than 0, which makes absolutely no sense, then return that the prior probability is infinity. And if it's not, return a 0. So why are we returning a 0, right? So if it's a flat prior, something like P of A is equal to 1, then if we do a logarithm, then log of P of A is log of 1, and log of 1 is 0. So we're basically saying return a flat prior if everything is like if everything physically makes sense, because having a negative variance doesn't really make sense. So now how do we define the log likelihood? So this is the most important function for optimization, and so here we have 4 parameters, right? So we have 4 parameters: the alpha, beta x, beta y, and the epsilon, which is the noise which we have added. And these are the parameters which we are trying to find. So we have a search space with certain bounds, and the Markov chains basically move all over the space, and they try to find the optimal alpha, beta, and beta x, beta y, and the epsilon values, which reduce which maximize the probability. So our goal is to find so this P is basically the value of P which we get is from the Markov chains, and using this P, so this will be a part of the random search process. So once we have a random set of these values, we try to generate some of our own data. So this is our model where we generate some data like alpha, beta x, and beta y. So this is the formula which we use. And so we know that this is the function, but we don't know the exact values of alpha, beta, and beta x and beta y. So this is our model data. And once we have a model data, we'll basically take a normal distribution and say that the mean is the true data and the model is the data which we have generated. And we are essentially saying for the MCMC to fix my model around a mean where the mean is the true data. So if we do end up finding such a distribution, right, we can find like the mean of alpha, which should be close to the alpha which we have used, and some variance. So using that variance, we can say the uncertainty of our mean. So if we take the log of this quantity, right, we want to have the mean is the true data and the x is the model data. So log of this would be minus log of, so this is sigma squared and d norm is sigma squared, and this is log of sigma squared, and we have like minus 0.5 in the middle. So this log likelihood is basically the log of this function where the mean is true data and x is the model data. That's it. And we return the log likelihood. So the idea behind this likelihood is MCMC tries to maximize the log posterior, and if we take the difference between the mean and the model data, then for a data where the mean is close to the model data, we want a higher likelihood, which is what's happening in this. So we have all these functions. So do these functions make sense, or was it a bit vague? Also here we do a sum because we are summing over like all the points which we have. So this is like the sum of all the samplers.
What exactly are we doing with the log function in the posterior there? Is it an assumption of what the distribution is, or what's going on there?
Okay, so usually while minimizing the Bayes rule, right? If we have a log, the P of A by B is equal to P of B by A into P of A. This would just be log of, like a multiplication would be converted to an addition when we do logs, right? So sometimes when things are too large, the optimization might just blow up. So in order to regularize the solution in a sense, we basically do logs, and we just take like log likelihood and log priors, and instead of multiplying the prior with the likelihood, the posterior would also be the sum of the likelihood and the prior. Does that make sense?
Yeah, I think so. And then we're computing those priors and the posteriors from where, or how are we getting those?
Okay, so the p value, so these are all the inputs, right? For all the these are the inputs for our posterior, and we are basically inputting the x, y, and the z value. So these are our data points, and p is the point which we get from MCMC, and we are basically trying to minimize the difference between the points which are MCMC is generating and the data which we have at hand.
Got it.
And we are doing that using this step. So okay, yeah. So you could have really complicated priors, and that would accelerate your solution. So you should play around by coming with different prior functions and seeing how it would affect the solution. So okay, so let's just run the solution, and if you remember from the GIF which we had a while ago, we had a 2D GIF and the Markov chains were going all over the search space, right? So to get an initial guess, let's actually begin with SciPy. So SciPy.optimize has its own regression function. So let's do SciPy's regression, and so these are the values which it throws out. So we can use these values as the initial estimates, and now do MCMC starting from these points. So that our results would be way better. Since we know that okay, let's go back and see what our parameters were. So we had alpha was 0.5, and beta x was 1, and beta y is 10, and epsilon was 0.5. And let's look at what SciPy is returning us. So SciPy says that alpha is 0.7, which is not true. So this should be 0.5, and this should be 1, and this should be 10, and this should be 0.5. So it's not exactly right, but it's also pretty much in the same space, right? They're all like pretty close to the true values. So now that we have this as an initial estimate, let's actually use MCMC and see how closer we can get to the true solution. So in the GIF which we had, we took 3 samplers, right? And in this example, let's take like 50 samplers. So we'll have 50 Markov chain Monte Carlo samplers, and we know that we have 4 parameters. So I'm saying we have 4 dimensions. So these 4 dimensions are alpha, beta x, beta y, and epsilon. So So based on these, we are initializing the results. We are initializing the initial states for the Markov chains, and then I'm saying basically generate me a Markov chain which has a length of 500, starting from these initial points. So these initial points are basically these points, but with some random variation. Okay, let's see how long it will take. Okay. Okay, so that was pretty quick, and we have like all these chains of Markov chains. So let's see what the Markov chains look like. Um, so the Markov chains, like they go in all the 4 dimensions. So we have the dimension of alpha, we have the dimension of beta x, beta y, and epsilon. So in this example, I'm basically plotting the 0th dimension. So this will be the all the chains corresponding to how they are varying in the alpha space. So this doesn't make any sense. So let's actually look at a single chain and see how it's varying. Um, okay, so this is our Markov chain, and so this is exactly like how like the thing which we have seen. So in the example we have seen that it went to A to B and C and so on. Right? So it's moving from alpha is equal to 0.75 to it's going to like 0.8 or something, and then 0.71 or things like that. So you get a sense of the Markov chain and how it is like spanning the entire alpha space. So I have also plotted the true value. We know that alpha is 0.5. So we can see how it's moving about the true value. So our goal is to, it starts at a really bad value and then it ends up at a distribution. So since one sampler wouldn't be of much use, let's actually use like 50 samplers, which is what we did in this step, where we have started with 50 samplers. So we have 50 chains, which are all beginning at the same initial condition, and they are moving to learn the ultimate distribution. So I think it makes more sense to plot these in different colors just to have an idea. So each color which you see corresponds to a different Markov chain, and you can see that towards the end they kind of form a distribution which is more or less centered towards 0.5, but you can actually make a more quantitative guess than just vaguely looking at them and seeing. So if you have a Markov chain, you can also plot the probability density function, since you have like all these values over a bunch of iterations, and then we can see the most likely value and the most the variance of each value. So we know that the Markov chain is varying in all these directions. So let's actually calculate the median of this Markov chain and uh, see if that would be close to the solution. So we could also take the mean or the median or like whatever. So usually, since we know that the distribution is more or less Gaussian, we can say that a median makes more sense, since a mean might be more uh, inflated by the extremes. So yeah, so if we have a mean, so we can see that this is the value which was predicted for regression, and the dotted lines are the uncertainty intervals. So this is something which would have been really hard to do with frequentist approach. So this is the z value against x, and this is the z value against y, and they do a pretty good job at forming the regression. So since it's more or less following the trend, and a more better way to understand the results would be to plot the corner plot. So here, this is our complete set of information which we have using a Bayesian analysis. So we know that the mean of alpha is around 0.5, and using this, we can form an understanding on the uncertainty with which we have arrived at our solutions. So based on the variances of these solutions. Okay, I think these plots don't make any sense at this point, but let me give more intuition behind that. So we have these four parameters like alpha, beta, beta y, and epsilon. And similarly, we have them on the same axis. So this corresponds to alpha comma alpha. So this would be a PDF, and this would be the conditional probability. Like this would be the P of beta x comma alpha. And so this is the joint PDF, and this is the independent PDF of P of alpha, and this is P of alpha comma beta x, and so on. So using all these plots, we can get a sense of how each parameter is related to the other one. So these are good plots since we know that they are all very independent of one another. If we had a variable which was highly dependent on the other, then we wouldn't have noticed a circle. It would be more smeared or something like that. So it looks like alpha and beta x are slightly correlated. So there are a ton of interesting there are a ton of interesting interpretations which we can make based on these plots. Yeah. Do you guys have like any questions on these plots?
So those circles, those are the like the projections of the distributions we're finding.
Yeah, they are like the two-dimensional Gaussians.
Got it. Okay.
And if it's something like this, we can see that it's more skewed, and it's probably like a flat rise, like a wake or something. But these look more independent. So if you look at the one-dimensional projection, right? So something like this is like very skewed to this side, and it's more left-leaning and things like that. So you can make like a lot of observations of your parameters and data, which wouldn't be available in a frequentist setup. So that's pretty cool. Okay, I'm going to stop the record. I think that's all the things which I had to talk to you. So let me just stop the recording. And